All right, so this type of question, this is one that personally these kind of bug me just because it seems like there's so many possible answers or, a couple that you go back and forth on. And a lot of times it's just like, which one is the best out of the available options because it's not always going to be immediately clear which one you should select for your answer. So we'll just run through it real quick. Normal distributions. This is a question all about normal distributions, so I'll just draw one down here. The mean and the median are equal in all normal distributions. And we know that normal distributions are symmetric and unimodal, which means the mean and the median are going to be equal to each other. We're not talking about them being approximately normal, they are normal. So we're looking for what's incorrect here. That one is correct, so that's not going to be the answer. Okay, and there you go. Yeah, so for some people it's reading the question itself wrong. Okay, a normal distribution is completely determined by two numbers, its mean and its standard deviation. All right, the mean will determine for this normal distribution, where is it located left and right? Like it could shift left and right depending on where the mean is. But the spread itself will be determined by the standard deviation. So you could have a spread that looks like this. It could look more like this. And that's going to be determined by the standard deviation. So those two numbers will basically confirm, what the shape and location is. So that is correct. Those are the only two numbers we need. All bell-shaped curves are normal distributions for some choice of mu and sigma. This is the kind of statement that kind of makes me kind of get skeptical a bit. And when it says all bell-shaped curves, all is these all or nothing questions, kind of in a different context. We did see one right here. It said all normal distributions, but this one right here, all bell-shaped curves, which seems like a much broader category, are normal distributions. So we'll come back to this one, but that might be one that I would kind of go back and forth on. Virtually all the area under a normal curve is within 3 standard deviations of the mean, no matter what the particular mean and standard deviation are. This is true according to the empirical rule, or the 6895, 99.7. I think it's fair to say that 99.7 is virtually all of the area. They're not saying all of the area, otherwise we'd know that was incorrect. But virtually all of it, well, 99.7 qualifies, so that one is correct. And the last one, standardized scores, z-scores, have a normal distribution only if the original distribution is normal. Remember, your z-score just transforms the data, transforms the distribution. It will basically shift everything over and then change the skew, or not the skew, but change the standard deviation based on whatever we multiply by. So when we subtract the mean, we're shifting it. Whenever we divide by the standard deviation, we're changing the standard, the shape of the distribution. But at no point are we changing the essential characteristics of the distribution. So if it's skewed to begin with, z-scores are just going to show us a standardized skewed distribution. So the underlying distribution has to be normal, has to be true. So that really only leaves us with this C. Again, that one might seem like it's a good choice. This might be one of them you read all 5 and you're like, all of them's incorrect, but one of them's got to be incorrect. And it turns out this one is, and this comes down to the fact that there are bell-shaped curves that are not normal. We looked at binomial distributions that are almost normal, and you see the histogram where it's nice and it looks fairly normal, but we don't have enough for it to be considered normal. But it is still a bell-shaped curve. So binomial distributions, there's another one, if you do more stats, called the Poisson distribution. Same kind of thing going on. So I think the takeaway from this is when you see the all or nothing, like no bell-shaped curves are this, all bell-shaped curves are that way, that might be one you want to put a star next to. It's not necessarily the answer, but it could be. All right, so last Friday, see, it's so Monday, I can't even remember what the last day of the week was last week. Last Friday, we didn't do our progress, and so we're going to do that. We have a little bit to talk about at the beginning. We're going to wrap up all of the learning for this quarter today. This is the last day you're going to learn something new. Tomorrow is going to be entirely practicing chapter 18 stuff. And I'll talk more about the test on Wednesday. Thursday is going to be review for your midterm, and Friday is the midterm. All right. If you cannot be here on Friday, then you can do the midterm next week. I know it's later than when grades are due, but if it affects your grade, then I'll just contact the front office and have them change your grade for you. Okay, so let's start with this. Of course, your favorite thing to do, I know it, whenever we complete a test, we started up here at Lee's Ferry and we've made it all the way down to Elves Chasm. How exciting, how very exciting. All right, oh, I should also point out that at the end of Unit 12, we're not going to be here at Pierce Ferry. We're going to be at Separation Canyon. So the last little bit of our adventure through the canyon is actually AP review. So just in case you're wondering, you weren't wondering at all, but now you know. So here's just a nice little scene of Elves Chasm. All right, so that's our progress. Now this, I don't have anything on this sheet, on this page, but it's worth talking about the AP formula sheet in Unit 7 test a little bit. So right here, this is the Canvas page. A lot of you, I hope, have already done this. I have a feeling some of you have not. The AP Statistics formula sheet has been there all semester, and maybe you've downloaded it, but you've never thought to go back and refer to it. But I thought it was worth looking at for just a second. And what we've got here, you can see where we started the semester. We've got our descriptive statistics. We've got a formula for the mean, standard deviation. We've got our regression, linear regression going on. So you've got your linear regression equation. This one right here that we use when we're trying to find the y-intercept. We've got our slope of the regression equation right here, and the correlation coefficient, which you'll never need to calculate by hand, but it's good to know where it comes from. Then we've got probability. Now they give us the general addition rule, and they give us conditional probability, kind of the way of showing that. But they also give us our probability distributions when we've got binomial or geometric. You can see the generic equation for like basically your PDF function right here. This is how you calculate it by hand. This is how you calculate your PDF function by hand for geometric. But then of course it gives us the mean and the standard deviation of those distributions. So if you need to remember that stuff, if you need to recall it, have this formula sheet ready. If you have two devices, have this pulled up on another device, whatever works for you. Print it off if you can. There we are. We're going to be getting into this stuff more, the standardized test statistic. We'll see that very soon. Confidence intervals, that's what we're going to start with right after fall break. Chi-square will come later. But then we've got right here, what we learned on Friday was this stuff right here. And notice that, I mean, you might not remember, but we talked about the mean of means. The mean of the sampling distribution of means right here is just the population mean. The standard deviation of a sampling distribution of means is, you know, the population standard deviation divided by the square root of n. It's here, but we're dealing with, you know, you can see there's two populations when we get to that later. So you don't, these are not secret formulas. You can look at these already and try and figure them out. So the whole point is make sure that you guys are looking at this and referring back to it, because there is a lot of useful stuff here. The last part of the formula sheet includes some tables, which some of these tables might not be super helpful. This one right here is called the T table. We'll get to that later. And that's going to be something that you'll probably refer to at least a few times. And then right here is chi-squared, which that will come later. So really useful stuff. I know it's probably not something most of you need to hear, but it is worth mentioning that this formula sheet is just a one-stop place to get a lot of your, just a reference for everything that we've done throughout the year. There are some things that weren't there, like you'll notice they didn't have the general multiplication rule on that formula sheet. So that will be something that you'll need to kind of maybe add to it whenever you start taking the test. All right. So I don't know how much more to say about the formula sheet. One thing kind of tangentially related is next week, whenever we have the Monday, Tuesday, and Wednesday that are half days, it's going to be shorter classes. And what we're going to do during those days is we're going to look over FRQs. And really the theme of that is going to be kind of review of units 1 through 7, while at the same time looking at what does a good FRQ response look like? What do you need to have in it? I've been very lenient in the grading, and maybe I have not been very good about really giving you a good idea of what to write for an FRQ. So I want to spend those 3 days working on that. Okay, then Unit 7 test. That's going to be Wednesday, but I understand it's going to be hard to take a test on Wednesday, me grade it quickly, do a quick turnaround and decide, oh, I want to do a retake on Unit 7 and have that done the next day. So Unit 7 test is going to be a little different. I don't know exactly what that means, except that it's not going to look like your Unit 1 through 6 test. And ideally, this is set up in a way that it's going to be very possible for you to have a good grade on this Unit 7 test. So that could mean a take home. You'll definitely have information on this tomorrow in class, and it might have some kind of take home element to it that you work on it tomorrow night, come to class ready, FRQs the next day. But it could look like something different, okay? Just keep in mind, you'll know tomorrow more about that. I've got some ideas in my head. So there won't really be a retake opportunity for this test, but it's also intentionally going to be designed so that you should be able to do well and have the opportunity to really think for a long time on it. Fun stuff. If you have more questions about that, you can stick around. We can talk about it more. Okay, so we're going to consider this scenario, and we'll worry about this link in just a minute. Suppose a large bag of Reese's Pieces has 1,000 pieces in it. The manufacturer says that exactly 40% of the candies are orange. If we select a sample of 50 pieces, how many will be orange? So we're going to let random variable x equal the number of orange candies in the sample. So that's the scenario. And what we're going to do is we're going to, first of all, consider what kind of probability distribution this will be. And we talked about binomial or geometric probability distributions. What kind of situation does this one seem to be?
Binomial?
Binomial. It is binomial. I'll go ahead and give you that because there seemed to be just a little bit of hesitancy there. So just to confirm, you were thinking of it right. Now, anyone, why is it binomial and not geometric?
Because we're not looking for the first success out of a certain number of successes.
Right, with geometric, it's always the first success, just like you said. What is binomial looking for?
The amount of successes in a certain number of trials.
There you go, number of successes out of n trials. All right, so that's what we're dealing with binomial. Yeah, we've got a set number of trials. In fact, we've got this bins that we use to make sure that we've got the binomial setting. Is it binary?
Yeah.
Yep. A success is
Orange.
orange. So that means not orange is a failure. All right. Independent.
Yeah.
It is independent. I think it's fair to say that no matter what you pull for one candy, the next one is not going to be affected by that. And of course, these two, the independent and same probability, I'll go ahead and say that's true. These are kind of affected by that 10% condition, 10% rule. So as long as we're not pulling more than 10% of all the entire population. So we got a sample of 50, but is that 50 more than 10% of population? No.
It's 5%.
It's 5%. It's either 5% we're talking about the 1,000, or we could go even further and we could say really the population is all the Reese's Pieces in the world, in which case, yeah, there's no way we're getting close to 10%. But even if we're talking about the 1,000-piece bag, because I think it's probably fair to say that's a random selection from all the Reese's Pieces that exist. Anyways, yeah, we are not exceeding the 10% condition, and we can use the binomial setting. And yes, we do have a set number of trials. Okay, so we're pulling 50. Okay, so this is more just review. Didn't want to spend a long time on this. So we know we're dealing with a kind of a binomial setting. We're going to be looking at binomial probability with this a little bit. And before we jump into that, we're going to actually run, this is really a simulation. So we're going to run a simulation, and I'll post this link in just a second, but I want to show you what this gives you whenever you click on it. You can actually see all your Reese's Pieces up here. And remember, it tells you the probability of orange, and it told us our probability was what?
40%.
40%. And there it is. So you're going to have a 0.4 probability. All of us are going to have a 0.4 probability. Our number of candies in our sample was
50.
50. So I'll just draw one sample. It's going to be a little choppy, but you'll see what's going on. Taking a sample for us. And out of this, it's taken a second to go. So in this last example, I got 21. Now you don't need to write this one down, but I got 21 orange candies. And what I want to do is I want to run this 5 times total. Now you can either do this, just hit draw sample again and just do this 5 times, or you can just do another 4 after that. Or when you get here, you can just say, do 5 of these for me. So whatever the case, you can see how to do that. So I want you to each get your own 5 samples of 50 each with a 0.4 probability. Let me paste this link in the chat and you guys can go for it. The next thing we're going to do is we're going to plot our results onto the dot plot. And before you start putting these on, keep in mind that this have weird spacing. So here's your 13. This is 15 right here, 17. And anyways, I'll just do these. All right. So why not? I'll just go up to 27 and 29. Okay, so those are where those are supposed to go. From here up, don't worry about these numbers on the side. You can just put your dots onto it. So we're going to try and keep it organized. So for me, I got 3 21s. So I'm going to put 1, 2, 3 dots right there for 21. I got a 16 and an 18. So a 16 and an 18. If you guys could fill in your dots that you got as your results. Okay, so we can see everyone's got their data put in. For whatever reason, we're not getting many right at 20, but you can see what's happening is that we are getting, and looks like someone got 11. That's crazy. We are getting what appears to be a normal distribution, which hopefully does not come as any kind of shock for you guys. You're probably expecting that, but we can see what's going on. Now, this does have a mean, all right? And we're going to say the mean is right here. In fact, we're about to find it. Spoilers, the mean is 20. And it does also have a standard deviation. And this we will calculate. But we can describe this normal distribution with those numbers. And yeah, I mean, when we get those numbers, it should kind of make sense. We can almost superimpose that. So let's jump ahead now. And I'll get rid of all this. It was a beautiful graph you guys created. Don't worry, you'll get another opportunity. All right, so let's find the mean and the standard deviation for the distribution of x. And to do this, we are going to remember that this is binomial. And the binomial distribution has a mean and a standard deviation. In fact, I'm going to see if you guys can either look this up, or if you remember it, you can just write down the formula for the mean and the standard deviation for a binomial distribution. So we got our mean is n times p, the standard deviation is n times p times q, the square root of all that. Of course, another way to write that is n times p times 1 minus p. That's what q is. It's the probability of failure. So we can just plug these numbers in. We know what our n is. We have a sample size of 50. So this one right here, 50 times our probability is 0.4. So here, when we calculate it, it is going to be a mean of 20. So you guys can now plug the numbers in here to find the standard deviation for this distribution. So 23.464. So if I went back to that, I already deleted all the points, but if we had those again, we could model this and we could say this is a normal model with 20 as the mean and 3.464. And that would be our normal model for that binomial. Okay, so that's all well and good. Now we're going to look at some other stuff going on. So you had 5 results from your simulation. And what I want you to do is convert all of these into the proportion of orange candies. So and we'll talk about the p hat in a second, but how will we find the proportion? So let me start with an example. The very first result I got was 21 orange candies. How do I convert that into a proportion? What calculation should I do?
Divided by 50.
Divided by 50. All right, when I do that, that becomes 0.42. All right, so you can do the same with your 5 results. Of course, yeah, just take a minute to do that. So it is worth pointing out that this is p hat, okay? And what this would be is 0.36 right here would be p hat shown like that. Again, if you read, you're already familiar. This is the sample proportion. I got a sample of 50. I'm looking at counts. When I'm not averaging anything out, I just counted how many were orange, how many were not. And the proportion of oranges out of this one sample was my p hat for that particular sample. We have, just to jump ahead a little bit, what we have for the population is just p. That's a population parameter. There's a lot of just using a p in statistics, so you have to just consider the context. So we're going to be dealing with letter P for the population proportion quite a bit, and you'll see that, well, you'll see it a lot. So just be aware of it. Okay. So on the next page, we have a new table here, a new graph. And so I'm going to take my proportions and I'm going to plot them on here. So I got 0.42 3 times. I got a 0.32 and a 0.36. And now you guys can add your proportions. If you are still adding dots to this, that's fine, but we can still see what's going on. This is creating an approximately normal distribution right here. And we can see that it's going to be centered around here. We'll talk about the actual mean and standard deviation. So the fact that it's centered around 0.4 might not come as a surprise to people. And I hope for most people, if you're thinking through it, that 0.4 makes a lot of sense for you. But one thing that's definitely changed is the standard deviation. Before it was 3.464. We're talking about the number of successes will vary by that amount. But now we're not talking about that. We're talking about the proportion. So that's going to be some value that is not, it's some decimal value. And we'll figure out what that is here in just a minute. But what we have, each one of these dots, it's worth mentioning, is we're talking about each dot represents a p hat. It's a sample proportion. We had to take a sample from a population. From that sample, we had to figure out what proportion were successes. And then that, if we count up these dots, I don't know how many are here, but 50 dots at least. All these dots represent, maybe not 50 exactly, but anyways, they all represent a different sample that was taken with a different p hat that was calculated. So there we go. That's kind of a takeaway from this. And now we've got that beautiful looking graph that we're going to get rid of. But we can continue with that in our mind as far as what the graph looks like. We're going to find the new mean and standard deviation. So we need to think about what we just did. We just took the mean from before, which had this formula, n times p, and then to get the new mean, maybe I'll do it this way. To get the new one, we took that mean, so I'm going to call this the mean of our sampling distribution of proportions. It's going to look like that, is going to equal the mean that we had before, n times p, but now we divided by, we took every one of our outcomes, right? Like, so I had the 21 and I divided by 50. And then you guys had different outcomes. You might have had 20 or 23 or whatever the case, and divided by 50. If we do that, we're really just rescaling this. I'm going to divide everything by n, which is at 50. So of course, n times p divided by n is just going to be p. And now what we're referring to is this represents our population proportion. That's what the p means here. Okay, so pretty straightforward. So if we took the n times p was 20, and we already calculated that one before, times let's just plug these numbers in. I'm not plugging in correctly. All right, so if I had 50 times 0.4 divided by 50, and those cancel out, and I'm left with just 0.4. And that's what we got as our mean. Okay. So, and we'll summarize all this on the next page. The standard deviation is the formula that was n times p times 1 minus p. Now, for the standard deviation of our sampling distribution of proportions, what we wanted to do was take that, which is n times p times 1 minus p, and we wanted to rescale it by dividing by n. When I rescale this by dividing by n, I can just put this all under the same radical, n times p times 1 minus p. And when I bring n under the radical, I have to square it. So it's n squared. Hopefully you can see algebraically what's going on with that. So the n up top and the n down below will cancel out. We're left with p times 1 minus p divided by n, and then the square root of all of that. And this is, if you go back to that formula sheet, this is the formula that we have for the standard deviation for a sampling distribution of proportions. So for our particular case, this is not something we're just going to figure out in our heads. We're going to do our p times 1 minus p, that's 0.4, times 0.6. And we're going to divide by n, which is 50, and then take a square root of the whole thing. Right. And anyone can feel free to write in the answer once you've gotten it. Okay, so it's all calculator work, for this, but yeah, you do get 0.069, and now we can kind of talk about what these numbers mean. If we go back, I know we don't have all the data points on it, but if I go back to this graph, I will just write over here that the mean for our proportions is 0.4. Standard deviation for our proportions is 0.069, and we can kind of erase the rest of this over here. So we should find, we'll have a little bit of stuff left over, but whatever. We're going to have our distribution center right here, something like that. And the standard deviation is going to be that 0.069, which is about 7%, if you want to consider it that way, 7 proportion. So it's going to go about that far is the standard deviation. So another way of thinking about this, if I just summarize it to 0.07, that means 0.4, well, 7 away from that is 0.33. And then, of course, 0.47. If I go even further away, that's 0.26. And then 0.19. 0.26 and 0.19. 3 standard deviations. Everything should fall within 0.19. And if I keep going, that's going to be 0.61 if I go further up. So here's the next standard deviations away, 0.61. So within these two values, we should have 99.7% of all possible sample proportions that could arise from a sample, if that makes sense. Okay, so that's a takeaway from this. All right, now we can kind of summarize this real quick. I'll clear all this off. And this is the formula. These are the formulas that we just came up with. Again, I pulled these straight from the formula sheet. So they're there. You don't have to have them written down. You just need to have access to that formula sheet. The formulas we learned last Friday look like this. When we're looking at means, and notice again the notation here. That's the mean for proportions. Here's the mean for means. Here's a standard deviation for proportions. That's the standard deviation for means. So it's the means, this side, these two are not too complicated, but these formulas over here on the right get a little bit, I don't want to say too difficult. They're more difficult. They're really not that bad, but you're going to probably want to refer to them Okay, so there we go. Let's see what else we got here. The last thing, what is the shape of this sampling distribution? So someone can shout out, what shape did we end up with?
Norm.
Normal. It was approximately normal. It's normal. It's good enough. We can consider it normal because it met the large counts condition. Again, this isn't a formal name. Neither is the success failure condition from the book an official name for it. Oops. But we have to make sure that we have a big enough sample size for this actually to work. And we're going to talk about that again in just a minute. But if I've got a sample of 50 pieces with a population proportion of 40%, well, n times p must be greater than or equal to 10. N times 1 minus p must also be greater than or equal to 10. And that's a condition we learned last chapter, chapter 17. So if I just plug this in, 50 times 0.4, and that is going to be 20. Has to be greater than or equal to 10, and sure enough, we did. We have at least 20 successes we can count on, or sorry, at least 10 successes we can count on. And of course, that's going to be the harder one to meet, so this one's definitely going to make it work. So 50 times the probability of failure is 0.6, which is going to be 30, which is greater than or equal to 10. So we've met both of these. It is large enough. This is going to be approximately normal. We can use our normal calculations. And here is the upshot of all this. We are going to be using these formulas to determine what our normal model looks like. So in this last example we did, our normal model for the proportions was 0.4 is the mean, and 0.069 for the standard deviation. And we can use, at this point, normal CDF calculations because we've shown that it meets the large counts condition and a normal model is appropriate. All right, so I said that was the last one. Here's the real last question before we move on to the final bit. Okay, so I've got the normal model right there. I'll just leave it up. So now the question is, what's the probability that a sample proportion will be 45% or greater? So what we, again, when we went back to the table, to the graph, what I showed was that all of your sample proportions should be really close to 0.4, but some of them will be away from that. And 0.45 is going to be somewhere about right here, because the first standard deviation right here is going to be 0.469. So we want to find the probability of getting 0.45 or greater, and this should look awfully familiar for you guys. It's just any of those outcomes, and we're doing a normal CDF calculation. So see if you can figure out what that proportion is going to be, or the probability of getting greater than 45%. And that is the probability. We did not, and good job, Andrew, we did not go through and do step by step on this. So there might be some people who kind of forgot how to get this done. What do we need to do first?
Find the z-score.
Find the z-score. So there it is. And I'll just do this real quick. It's 0.45 is the data point of interest right there. The mean is 0.4. Standard deviation is 0.069. And again, just to finish this quickly, it's going to be 0.724. All right, so that is your z-score, and then you just need to do your normal CDF, where 0.724 is your lower bound, and it goes up to 999, and honestly 999 is plenty. 99 is okay. That doesn't matter. It goes up toward infinity, and you should get 0.234 when you do that calculation. So there it is. This is going to be the main calculation you guys will do for the rest of the year. All right, you're going to be doing z-scores over and over and over again with normal CDF calculations. You've done this enough, you've already learned it, so if you just get reacquainted with it, you will see this quite a bit. And that's why I keep telling people that the second half of this class is a repeat of the first half, just the same stuff comes up over and over again. So good times on the way if you enjoy normal CDF calculations. And that's not abnormal at all. Okay, central limit theorem. This is kind of they call this the fundamental theorem of statistics, the main takeaway that's going to be foundational for everything that we do. And that is that when you have, states that the sampling distribution model of the sample mean and proportion from a random sample is approximately normal for large N, regardless of the distribution of the population, as long as the observations are independent. So there's two assumptions here. One was that the observations are independent, so we need to have that. The second one is that we have a large N, and we will check for that. We already know about the large counts condition when we're dealing with proportions. When it's means, we'll look at other things, and that will be a major thing that we come back to. But assuming those are met, here is the takeaway. Regardless of your population distribution, and here we have a skewed left distribution, if that's our population and we keep trying to get a sample mean over and over again, and we create a sampling distribution of the mean, the sampling distribution of the mean will be normal. So that's why we work with sampling distributions. We can always use normal calculations with those. If we don't have that, if we don't have a sampling distribution, well, that requires some other calculations and some other things factored in. But we can always turn any population distribution into a normal distribution by taking a sampling distribution of it. I just said distribution a lot, but are there any questions? Okay. So this, I'm going to repeat what I basically just said. When we're looking at sampling distributions, the resulting distribution will always be approximately normal. And we can just call it normal as long as the condition has been met. But yeah, approximately normal. The mean and standard deviation will be determined according to whether we are creating a distribution of proportions or means. And the population proportion or the population mean will always be equal to the sampling distribution mean. And that's assuming that it's an unbiased estimator. The sampling distribution standard deviation is not going to be the same as the population standard deviation, and we have formulas for that. It can be derived, remember, it's going to be basically divided by n, divided by the square root of n, all that fun stuff. And the central limit theorem, the fundamental theorem of statistics, guarantees that sampling distributions with big enough n will have normal distributions regardless of the population distribution. Okay, so now with the last little bit of class, we're going to go over a few things here. All right, so some of these are more conceptual type questions. Some of them we're going to have to do some calculations on. This is going to look very familiar to begin with. The candy company claims that 10% of the M&Ms it produces are green. Suppose the candies are packaged at random in small bags containing about 50 M&Ms. Hey, this is looking very familiar. A class of elementary students learning about percents opens up several bags, counts the various colors of the candies, and calculates the proportion that are green. If we plot a histogram showing the proportion of the green candies in the various bags, what shape would you expect it to have?
Normal.
Okay, and it could be normal. So let's just kind of think through this real quick. Here's 10%, 20, 30, 40, 50, 60, 70, 80. It doesn't really matter. So here's 0%, here's 0.1, 0.2. We certainly expect it's going to hover around 0.1. Now, in a bag of 50, is it theoretically possible to get 0 green candies?
Yeah.
It is. We wouldn't expect it really, but we might. So we would expect this to kind of maybe have some zeros and then come up and max at about 0.1. Now, we need to think of the other side. Certainly having 20% of them being green is realistic to assume. Could we theoretically have 0.3, like 30% of them be green?
Yeah.
Yeah, and so just thinking about this, we could have 30%, since it's just 50 in the sample size. 0.4 is unlikely, but what we might expect is something, we're limited on the low end, right? We can only go down to 0. So it's going to drop off right there. But here, it could theoretically stretch out a little bit, maybe like that. And what we have is a skewed right distribution. So we would probably expect it to be skewed right just a little bit. And now the question you might be asking is, why is this one going to be skewed right when we were looking at the Reese's Pieces and it wasn't skewed? Well, large counts. Let's see what's going on with this. We have n times p has to be greater than or equal to 10. N times 1 minus p also has to be greater than or equal to 10. So our sample size is 50. The probability of success is 10% right here. So 0.1 greater than or equal to 10. Well, that's 5. We didn't meet the large counts condition. So in this case, we're probably going to have a skew. It might not even look this extreme. It might barely be a skew. It might look more like this, something like that. But we would probably have a little bit of a skew, which is going to throw out the calculations, because here's the idea. We want to turn this into a normal model so we can do some calculations, but this isn't exactly normal. So if I wanted to figure out the probability of getting 0.18 or higher, well, that calculation isn't going to turn out correct because there's a skew. So that's why we're saying we need to have a big enough sample size. Of course, this is going to be the complement to that, so it's going to be 45. So that one is easily met. But we didn't meet the large counts. So could we use a normal model here? Not really. But kind of on this note, as a brief aside, if you came across an FRQ where they wanted you to do a lot of calculations, but it failed one of the assumptions, like the large counts here, what you could do is you could continue on and do your calculations and just make a note to say, we didn't actually meet this condition, so the numbers that I'm about to calculate aren't exactly accurate, and take results with a grain of salt, more or less. So, and hopefully we have a lot of examples like that. So, technically here it would be skewed right, and it would be, no, we couldn't really officially use the normal model. But the next two require us using these calculations anyway. Where should the center of the histogram be? Well, this is going to be proportions, so the center should be just at 0.1. We know the population proportion is 0.1, so our sampling distribution should be centered there as well. What should the standard deviation of the proportion be? And now we're just doing our calculation, which is p times 1 minus p all over n, square root of all that fun stuff. And I got 0.0424. Okay. And just as another really brief aside, and I like telling you a bunch of stuff about stats that you won't need to know for the test, and you won't need to know for anything in this class either. When you have a it doesn't matter what the distribution is. So you could have like a multimodal distribution, something like this, all right, something really weird going on. And let's say the mean of this is, well, probably wouldn't be there. Let's say the mean is right here. You can count on 75% of the data being within 2 standard deviations of the mean because of something called Chebyshev's theorem. You used to have to know this for stats, and now you don't. But it's just an interesting thing to know that even when you have non-normal distributions, there are some rules that they follow, as you might imagine. So it is kind of an interesting thing there. All right. But again, don't worry about what we just talked about. I just thought it was a worthwhile thing for you guys to hear. All right, so now we're going to do this again. We got 200 M&Ms. Just real quick, are we going to meet the large counts condition for this one?
Yeah.
Yeah, we should meet it. So N times P, and the probability hasn't changed. So that's going to be 200 times 0.1, which is 20, which is greater than or equal to 10. That was really the only one we need to worry about. So good. It's appropriate to use a normal model. We passed large counts condition. The other would be 180, which is definitely greater than or equal to 10. So now we're going to use the empirical rule, the 68, 95, 99.7 rule, to figure out how this proportion might vary from bag to bag. What they're asking us to do is come up with the normal model for this. We know the proportion is going to be, or sorry, the mean is going to be 0.1. So now we need to find the standard deviation. You guys can do that calculation on your own. All right, and that's what I got. Hopefully everyone is on the same page. If you become a professional statistician, you have to know how to draw a normal model really well. I kind of suck at it, which is why I could never be a professional. All right. So we can always start off with this. We know that it's going to be, this is going to be centered at 0.1. All right. So we've got our standard deviations right there at the inflection point, and then we just go out at same intervals away. And this is something I have not been doing a good job of having you guys do, but drawing your normal model with the standard deviations is the best way of showing AP that you know what you're doing. Okay, so right here, if 0.1 is the mean, I can just add the standard deviation as I go up. So that's going to be 0.1212. Add another onto it. That's 0.1424. And that's not hard to add on, so I'll just do the last one, 0.1636. I'll go the other way and do that as well. So I believe I did that math right. In fifth hour, I just couldn't seem to do math correctly at all the entire time. So we know that 99.7% of all of our proportions, sample proportions that we get from 200 M&Ms is going to fall within 3% for the sample proportion and 16% for the sample proportion. So if we ever got anything beyond that, outside of that range, that would be highly unexpected. Okay. So how would this model change if the bags contained even more candies? What do we think?
Would the sample mean get closer to the population mean?
That's a good thought. It should theoretically be the same no matter what. So the sample mean our sampling distribution mean should be at 0.1 no matter how big the sample size is, if we get enough samples. And just before anyone else answers, I'll say that doesn't matter even if our sample size was 2, right? That's not big enough to make it into a normal model, but even with the sample size of 2, our mean should, our sampling distribution mean should match up with the population mean, or in this case, the population proportion. That's a good thought.
The standard deviation will get smaller.
Standard deviation will get smaller. And keep in mind for both of these, and I'll show for both. So for sampling distributions of means, it's divided by the square root of n. For standard deviation of sampling distribution of proportions, it is also divided by square root of n. That's going to be p1 minus p divided by n. Okay, so we have an inverse relationship with n in both of these. As n goes up, then your your standard deviation will go down. As your divisor gets bigger, your quotient gets smaller. And that's the way it works here. Okay. Let's see, I'm going to skip that one and skip that one. And we're just going to look at this one to end the day off. Okay, so we've got statistics from Cornell's Northeast Regional Climate Center indicating that Ithaca, New York gets an average of 35.4 inches of rain each year with a standard deviation of 4.2 inches. Assume that a normal model applies. Okay. So in this case, we don't need to worry about, well, anyways, a normal model applies. I'll just be quiet. During what percentage of years does Ithaca get more than 40 inches of rain? Okay, I actually don't know if I want to do this calculation. It's going to have to be a normal CDF, right? We got to find our z-score, 40 minus our mean. I'm not going to actually do any more than this. Divided by the 4.2 standard deviation. That's chapter 6 stuff. You should be able to find that percent. Less than how much rain falls in the driest 20% of all years. This is worth talking about. And remember, if we're given the percent, what function are we using? Anyone remember this? All right. Inverse norm. Feels like a lifetime ago, when really it's only like a month ago we were doing this. Inverse norm we can use to figure out if we know the area. In this case, it's the driest 20%, which means it's the lowest rainfall 20%. So in our normal model, it's going to be the 20% that lives down here, or about right here, right? So 0.2 is my area. If you have the advanced calculators, it'll be your 0.2 with the left tail. And that gives me my z-score of negative 0.8416. And now I can use my z-score calculation, negative 0.8416. I know the mean is 35.4. I know the standard deviation is 4.2. So this is going to tell me when I solve for x right here, what is going to be the rainfall amount that is kind of the cutoff point for the 20%. Okay, so we can do that math. And I got 31.87 inches. Again, just a nice review of some stuff we were doing in chapter 6. For the life of me, just at this moment, I can't tell you how many times inverse norm might come up in the future. So it might come up, it might not. A lot of times it's just the normal CDF calculation, but it's good for review. All right, so now let's look at this. A Cornell University student is in Ithaca for 4 years. Let Y bar represent the mean amount of rain for those 4 years. Describe the sampling distribution model of the sample mean Y bar. Okay, so we're dealing with means. So when we're describing this one, what we have is a, we'll do this more, but this is basically going to be a normal model. And we want to figure out what the mean for X bar and standard deviation for X bar is going to be. So the mean is just equal to the population mean. So that's still going to be 35.4. But our standard deviation is going to be the standard deviation divided by the square root of n, which is going to be 4.2 divided by the square root of 4, which is 4.2 divided by 2, 2.1. So our normal model right here, if we just describe it with our notation, is 35.4 for the mean and 2.1 for the standard deviation. And now we can just do one more normal CDF calculation. This is where we'll end it for the day, to figure out what's the probability that those 4 years averaged less than 30 inches of rain. So if I was to superimpose this distribution onto this one in the top right corner, it would look more like this. Let me get rid of that. All right, we're gonna have a smaller standard deviation. So now we're looking at wherever 30 ends up, if it's right around here, what's the probability of it being 30 inches or lower? All right, so let's figure it out. The z-score for this, no, erase some of this other work. All right, so the z-score right here is gonna be our 30 inches minus the mean, which is not changed from the population, 35.4, but divided by the standard deviation, which is now 2.1. Which gives me a negative 2.571 z-score. And with your statistical knowledge, you already know that's highly unlikely to get a z-score that low. So we can figure out exactly what the probability of getting anything from this z-score further to the left, which is not going to account for much. So it'll be normal CDF from negative 999 up to negative 2.571. And it's only 0.5% chance of happening, 0.0051. Okay, now this is a preview. We've done a few things in class today that are previews for stuff that's going to come up very soon. So if everything was kind of clicking for you today because you're like, oh, it's just normal CDF. Oh, it's that empirical rule with a 95% for the 2 standard deviations, all that fun stuff. If that is all working, then what we're doing starting after fall break is going to be just easy, okay? And I hate using the word easy, but I mean, just compared to other stuff, it will be easy. Okay. Any questions on this stuff? All right. There's your homework. Tomorrow's just going to be review of everything in Unit 7. I'll also give you kind of the rundown of what to expect for your test, which might include some stuff to take with you. I'm not going to give you a homework tomorrow night. The only homework you might have is part of your test, like I was saying. So just stay tuned and find out. But look over this stuff. And just on the last note about homework, if you have old homeworks that you still need to get turned in, please get those done. Old progress checks. grades are due on Friday. So if it is not turned in by then, it does not count. And have yourself a wonderful day. That's all I've got for you. I took up most of your day.